Okay, thank you very much for the introduction. So this work has been done in collaboration with Georgios Katsikas, Gerald Maguire, and Dejan Kostic. So today we have 100 gigabit networking cards, which are becoming a commodity in data centers. And those NICs have to dispatch dozens of millions of packets per second to many core CPUs, right? And both the speed of the Ethernet NICs and the number of cores are increasing dramatically, right? So the question that will animate us today, how to dispatch dozens of millions of packets to many cores, is a problem today, but it will be even more of a problem tomorrow. And if we ask that question, how to do high-speed packet processing to the state of the art, a lot of recent work in key-value stores, a lot of recent work in packet processing NFV will advocate the use of sharding, right? And all the recent network stacks are sharding. So what is this sharding about? To explain to you that, I will show you our sharding testbed. We've got a computer with 18 cores, and we have 100 gigabit Mellanox connecting 5 NICs, which we configure to have 18 receive queues, 1 per core. And we run our application pinned to each core in a way that it doesn't migrate. So that's the idea of sharding. You've got shards. You divide your server in shards, and when packets are received on a shard, they don't move out of the shard. So you can almost consider each core as a different computer. And the big advantage of sharding is that you don't have any shared data structure, right? So that's very efficient. Of course, there is one problem with sharding, or I wouldn't have a paper today. So we'll run an hyper client that will request 100 TCP flow to that machine, which will last for the duration of the experiment, right? And very important, to dispatch the packets to the queues, we use RSSs. Pretty much standard. Basically, RSS is hashing packets in a way that packets of the same flow go to the same core. And we plot a heat map of the load of each CPU core over time, we'll get this. And we can see that there is a lot of cores that are completely overloaded and cores that are completely underutilized. And that underutilization is bad because, well, you pay for those cores. They are all allocated, so if you're in the data center, you pay for those, but they're not really used. And maybe even worse, you've got a very high fail latency, because those overloaded cores, they will queue and they will drop packets that will read to retransmission, and some users will have a laggy feeling, a bad service. So what we propose in RSS++ is to tweak that hashing of RSS, I go back to the details of course, to rebalance some flows from time to time, from the overloaded cores to the underloaded cores. And that achieves a much better load spreading. It reduces the latency by, in this experiment, by around 30%, but more important, the tail latency by 5x. And why is it more important, in my opinion? Because there is all those studies by Google, Akamai, Facebook, which show that even than less 1 second latency increase, you can lose 20% or a high number of your users. But we can go further. We can completely schedule off all flows from some cores to achieve auto-scaling, basically according to the load. And in this experience, it allows to reduce 6 cores out of 13, so that's 1/3 of the resource, by raising the CPU utilization, because we've got this nice reading, so we can afford to raise the CPU utilization. Okay, so to explain a little bit why we saw this problem, what our RSS++ challenge, I've got to explain, of course, how RSS itself works. With RSS, the packet is received by the NIC, and the NIC hash the packets, the for tuple in general, so that means that the hash will be the same for packets of the same flow. And the NIC uses the last bits of this hash to select an entry into an indirection table. The indirection table contains the index of the queue that the packet should be delivered to. And in a sharded approach, we've got 1 queue per core, right? I'm going faster than my animation. Okay, so the problem that we saw in this sharding experiment is that some queue receive much more packets than some other. Right? That can happen for 2 reasons. First, hashing is not uniform spreading, right? So some entry of the indirection table get hit by more flows than some others. But even if hashing was super good, super uniform, you're still hashing in the internet on mice and elephants flow, right? So you've got a few huge flows, but a lot of small flows. And that creates this imbalance between the cores. So in a way, RSS is flow aware, purely flow aware, so packets of the same flow go to the same core, but it's kind of bad at load balancing. So we can also do the opposite, completely forget about flows, and just dispatch packets, for example, in the round-robin way, right? So we have the next to give one packet to one core, one to the other core. And NAT techniques achieve a very good load balancing, of course, but it's completely flow unaware. So packets of the same flow will get spread to all the cores, right? And we'll see the problem of that later. So we've got basically this balance between flow awareness and fine-grained load balancing, right? So what we try to do in RSS++ is to strike for the right balance between this load balancing and churning. And we do that by migrating some of the RSS buckets from time to time, right? So you remember that those buckets are used to dispatch, to select some queue according to the last bits of the hash. So if we rewrite an entry that dispatch packets from currently to an overloaded course to an underloaded course, that will shift some of the load of the overloaded course to the underloaded course, right? And we don't select entries like randomly. We use an optimization algorithm, which will tell us which buckets to move to which underloaded course to have the best even load as possible. We introduce one problem in RSS++, which is that we migrate some of those buckets, right? So that means that some flows will be handled by other cores. And for stateful use case, where you've got some per flow state, like NAT, DPI, network stacks, we implement a new flow table algorithm where you've got one flow table per bucket. So when you migrate a bucket, you can migrate the state with it. I'll come back to the details of that, and that compensates for the eventual migration. Okay, so how does RSS++ work? Well, it's based on RSS, of course, but what we do is that on each core, we maintain a counter of how much packets were received by each buckets of the indirection table. And from time to time, RSS++ balancing timer will run our algorithm. It's dynamic frequency, so if the load is really unable between the core, it will run the maximal load. We found that 10 Hz was enough. And it will learn slower if it's not needed. And that algorithm will use those number in the counter, so the number of packets received by each indirection bucket, and a certain notion of CPU load to compute for how much each bucket is accounting for in terms of CPU load, right? And then we use an optimization algorithm to try to minimize the load imbalance by migrating some of the buckets of the overloaded cores to the underloaded cores. And we present in the paper a formal definition of what is a variant of the multi-way number partitioning. But in practice, we don't use a solver. Why? Why? Because we actually don't care about the most exact solution, right? Because those counters, those packet counters, are a certain number at one tick, but at the next tick, they will slightly change. Like the flows come and go, etc. So even if you took a lot of time to compute the perfect solution of your optimization problem, it wouldn't be the real perfect solution at the next step. So in practice, we use a greedy iterative approach, which basically tries to find the right balance between moving not enough or too much buckets. And in 85% of cases, this iterative algorithm finished in one run in 25 microseconds with a very good balance, so we're fine in terms of performance. And then we can rewrite, according to the output of the algorithm, the rata table, and the interaction table, and we have two implementations of RSS++, one using the Linux kernel. To count the packets, we use a VPF program inserted, compiled and inserted directly in the running kernel using the Express data path, presented at a great conference last year. And we use, for the CPU load, the kernel CPU load, as you know it, from HTOP, given by the kernel. And then we write the interaction table using HHSUD API. And we've got a second implementation, which is using DPDK. And with DPDK, we receive the packets directly in user level, so we can count the packets using in-application function codes. And for the CPU load, as DPDK is using polling, it would be always 100%. So we use a proportion of useful cycles over all application cycles as the metric of load. Okay, I told you that we've got this little program we introduced in RSS++. We've got eventual migration of buckets. So some flows. So in the sharded approach, you've got one flow table per core. So what if green flow is received on flow table 1, then you decide to migrate the bucket that dispatch green flow to core 2? How do you find the state? Right? So one way to do would be to roll back a little and use a shared flow table among all the cores, right? But all those sharding papers, they say don't do that. So we do not do that. And what we do in RSS++ is to have one flow pointer table, which is the same size of the indirection table. And that flow pointer table gives us a pointer to the flow table. And we've got one flow table per bucket, right? And we use the same technique that the hardware does. We receive in software the hash as computed by hardware, so we don't even to rehash in software. And we can use the last bits of the hash to select which flow table should handle the packets. So when RSS++ tells to migrate buckets number 2 from core 2 to core 3, core 2 will stop receiving packets, core 3 will start receiving packets for that bucket, of course. And there is basically nothing to do. We don't have to move the state. The core 3 will look at the last bits and will find the right flow table. There is just one slight hiccup at the very exact moment where we write the indirection table. Core 2 could still be handling packets of the previous table because they were sitting in the queue. And core 3 could start, while core 2 is handling this packet, could start handling new packets. So we queue the packets of core 3 until we are sure that core 2 has finished to handle all of its packets of the previous indirection table. But this is actually a very unlikely case because the goal of RSS++ is to keep an even load between all the cores. So in average, we hope that most of the cores will start processing packets of the new indirection table at the same time. Okay, it's time for some evaluation. The first metric we use is a metric of load imbalance between the cores, and we'll count that as the number of packets received by the most loaded queue minus the number of packets received by the less loaded queue over the less loaded queue, which means basically that a perfect load balancing solution will achieve 0% imbalance, right? So all cores receive exactly the same amount of packets, and 100 means that one core has received twice the amount of some other core. And the first technique we'll evaluate is those packet-based methods. You remember, for example, round robin would achieve very good load balancing, but Nix cannot do round robin, actually. So some smart guys at Hotnets last year came with sprayer, and basically they abuse RSS to randomly spray packets all over the cores, right? And that achieves a very good load balancing. Sorry. And then for RSS, as we've seen already, the load balance is not that good. And sorry, I'm going a little bit too fast. One could say, okay, the problem of RSS is that it's hashing, right? What if for every new connection we select the best core, the least loaded core? What if for every new connection we dispatch them in round robin way to all the cores? And that is actually not working very well. And this results shows that basically we need migration. That stands for the migration ID. To achieve a good load balance, we cannot just do the best thing we can per connection. We have to migrate some connection from time to time to even the load. And that's how in RSS++ we can diminish the load imbalance by 12 times with an average of 5 times. Okay, so a great load imbalance, what does that help us to do to answer that question? We run a service chain. We do a little test case with service chain at 100 gigabit with a firewall and a NAT, right? And here you see the imbalance of the throughput of RSS. And you can see that it grows linearly, but at some point, it's like giving more cores doesn't help anymore, right? We cannot achieve line rate. Why? Because it's because of this hashing. Even if you give more core, it doesn't guarantee that you will take out an even load from the overloaded core. So some cores, even with 15 cores, stay completely overloaded and drop packets. And with RSS++, we have a linear scaling basically, and because we do spread an even load between the cores, and we have in the paper a comparison about those cases among latency, because the latency is also, even with 15 cores, much higher with RSS, because some queues are full while some other queues are empty. And what about those packet-based methods? Well, the problem is that you're basically asking for the worst case of contention, right? You imagine you receive a burst of 15 packets. Those 15 packets will be spread to all cores that will eventually process all the packets at the same time. So you will access the 15 cores will access the same part of the memory at the same time, which is asking for the worst case. And because packets can arrive to all the cores, we're forced for these kind of methods to use a shared flow table, which was proven to be that inefficient in all those sharding papers. Okay, so what I've presented here is a NIC-assisted scheduler, right, which is state-aware. Why is it very important to be NIC-assisted? Because it avoids the use of dispatching cores, which are real bottleneck as shown in the paper and in the previous sharding approach. And the fact that we avoid these dispatching cores allows to keep this sharding approach, and thanks to our state migration algorithm, we can avoid mostly any shared data structure. And all in all of this gives us an order of magnitude lower tail latency, while not dropping any packet, while using 25 to 37% less code. And with this, I will thank you. Oh, sorry. With this, I will tell you that we have two implementations, the Linux and the TPDK one, and they are fully available with all experiment scripts. And I forgot to put, but we have also the available and functional batches. So yes, with this, I will thank you for listening, and we'll be happy to take any question you may have.
Thanks a lot. Are there questions? Maybe I start with one question because you just had it on the last slide. Can you give a bit more details on your implementation? So what you need, is it, I understand that there's no extra hardware, or what you need, so basically you can realize this is typical DK?
Yes, so we only use RSS, right? We need to rewrite the generation table. So with DPDK, there is just code. With the kernel implementation, we have two small patches, which are mostly for performance. So you could achieve actually RSS++ fully without modifying your kernel. But yeah, so we don't need specialized hardware or anything, but that's one of the advantages of RSS++.
Is there any difference between the two options that you offer here? So,
well,
which one would you recommend?
Well, for really high-speed DPDK is proven to be very efficient. And then with RSS++, you can actually overcome the worst problem of DPDK, which is polling. So you're basically, if you run the machine like that with DPDK, you'll have 18 cores polling at 100%. So you'll kill your energy bill, and RSS++ will automatically use the less possible amount of cores by compacting the load if there is not much load. So we overcome actually one of the biggest problems of DPDK.
There's a question?
Yeah. Hi. Thanks for the talk. Very interesting. I have a question because for your flow migration, you said that you need a queue to temporarily store packets that are not handled by the current core. So is this queue pre-allocated, or you do runtime allocation, so just for the migration?
It is pre-allocated, so with each of the flow table, we have a little bit of metadata to handle this migration. So to know when the previous core has handled all the packets. And in this metadata, we've got this queue pre-allocated. But we're using for this implementation fastly, so it's basically a linked list, so it's already pre-made, there is not much allocation. So and that queue is only used by the core which is expecting its new packets, so it's thread safe, lockless. Well, there is no exchange between cores, so there is.
So there is no overhead due to
no, nearly no, because it's not, the queue does not exchange packet between cores. It's just for one core to just wait a little that the other have finished. So the core is just speaking to itself. Sorry, it's not very technical, but that's it.
Thanks.
Thanks for the nice talk. I was wondering, when flows move between cores, basically, what effect does it have on the application performance?
Very good question. So I would see two different cases. The first is when you've got a stateful case, right? So when you've got this stateful case, you'll have a small amount of cache misses when the state migrates, right? So we don't have then move or etc., but you'll have some cache misses. But in what we saw, having a few cache misses for some of the flows is much better than migrating all the packets between cores, for example, right? Yeah, that's for stateful cases. Even for stateless cases, like we have, I can show you a firewall test case. Okay, that will do. Firewall test case, so just look at the three top lines. We can see that the sprayer, the packet load balance, the packet-based load balancing method is running a little bit slower. Why? Because you have a caching effect. So it's always better to have all packets of the same flow following each other, because in the case of firewall, you do the lookup for the first packet, but then the cache time will be one for all the subsequent packets, or you can even have software caches. While if you spread all those packets to all cores will see different packets of different flows, so you'll be less cache efficient and you'll have more latency and slower performance like this. That's fine. Thanks.
Any more questions? If not, then thanks again.